Hey guys, welcome back to Fam Bam, and today we'll be discussing energy problems that use energy and dynamics. Okay, so an alternate method to solve many dynamic problems is the energy method. This helps you if your problem involves finding position or velocity, but does not work for finding acceleration. So the general work equation is the change of U, the potential energy, equals F times dr. And then the other equation we have is the gravity equation. So the UG equals velocity second over velocity first times mg dy equals negative mg change of y. And then this signifies V1, V2 is the total work by all forces. Forces from point 1 to point 2. And then here we have an example. It's an inclined plane with a spring and a block weight pulling down. The spring's K constant is 200 Newton meters, while the velocity is 5 meters, and the force is 10 meters. And this is the equation we'll be using, which is the total mechanical energy 1 plus the sum of the difference of the potential energy, and then from point 1 to point 2, and then it's T2, which is total mechanical energy 2. And so there's a lot of things going on here. We have the work being done on the block, the work of the spring, and the work of gravity. So here we have our 4 major components of the inclined plane. We have the work of the force, which is basically the gravity pulling down, and that's F equals 100 newtons. And then the UF equals 100. This is the equation we're going to use to solve the result now. We solve one component first, and then the next, and the next, and then in the end we add it all together to one big equation. And so 100 times S2 minus S1 equals 100 S2, and then S1 would be the spring constant, which is 0.6. And then for the component 2 would be work of block W, which is this one right here. And the equation is potential energy of the block equals the weight 10 times 9.8 parentheses times S2 minus S1 times sine of 30 degrees, which equals 49.05 parentheses S2 minus 0.6. And for part 3, we have the work of the spring, which is the potential energy of the spring equals negative 0.5 times 200 parentheses S2 minus 0.6 squared, which equals 100 parentheses S squared minus 0.6 squared. And then for part 4, this is the total, which is the really long equation, which is 0.5 times 10 plus 100 parentheses S2 minus 0.6 plus 49.5 times S squared plus 0.6 minus 100 times S squared, S2 minus 0.6 squared, which then turns into 125 plus 149.5 parentheses S2 minus 0.6 minus 100 times S2 minus 0.6 squared, which then equals 0. And here we're solving for S2 minus 0.6. So we have the equation S2 minus 0.6 equals curly bracket, negative 149.5 plus or minus parentheses 149.5 squared minus 4x parentheses negative 100 times 125 to the power to 0.5 power curly bracket divided over 2 times negative 100. You then get 2.09 meters, and then you cancel these out, and you get 2.69 meters for S2. And we also have a lab example. So for this, you would set up a cart and a ramp, and then you would add 2 1/2 kilogram blocks, regular masses, on the cart. You weigh the masses of the cart, and then the additional masses, and then attach the hook to the end of the spring, and then screw it to the top. And then from there, you would see the spring pulling down, and then that's your lab. Alright, thanks for watching.